So our next section is on what we will call families of functions. And so some basics to start with. The simplest form in a set of functions that form a family is commonly called the parent function. And so if my function is f of x, my set of functions will be y equals a times f of x minus h plus k. And so this is a general form of functions. And I know this is going to seem a little confusing for now, but I think over time you'll get the hang of it. One of the reasons we're doing this section by video is so that you can kind of keep rewinding and rewatch again in case it helps you get it. So when we make a change to at least one of the values above, a, h, and k, and that is called a transformation. Transformation. And so there are four types of transformations. A stretch, which could also be a dilation. A reflection, a rotation, and a translation. And so we'll get into all those different types as we go through here. A translation, which is the easiest and most basic, is a shift in the graph of the parent function horizontally, vertically, or both without changing its shape or orientation. And so from up above, the values that would change in the case of a translation are going to be h and k. And so h and k could change. The next type is a reflection. And a reflection flips the graph of a function across a line, such as the x-axis or y-axis or any other line. But for now, we are going to focus mainly, in fact, only on reflections across the x-axis or y-axis. We will not be doing more difficult reflections. Let me slide this up to make sure you can see that. So again, a reflection flips the graph of a function across a line, such as the x-axis or y-axis. If we multiply all y values of a function by the same factor greater than 1, that will result in a vertical stretch. And so this is going to be when something is happening to A, like you see above. And then a vertical compression reduces or shrinks all y values of a function by the same factor. And so this is when our a is between 0 and 1. And so this is also something that happens to a. So let's look at our first vertical translation. And we're going to look at lines first, although with lines, we could see both a vertical or horizontal translation in the same movement. All right, so if our parent function is y equals 2x, we want to see how y equals 2x minus 3 is related to the parent function. How are their graphs related? So the first thing we're going to want to do is graph our y equals 2x. And since it doesn't have an intercept, we can assume there's a plus 0 there. So that means our y-intercept is 0. And so since my slope is 2, I'm going to go up 2, right 1, and then I can draw my line. So there's y equals 2x. And hopefully you can see the different color. I'm going to draw y equals 2x minus 3 with my red pen instead. If this ends up not working, I'll switch to green for the next video or something. So again, my y-intercept is 0, negative 3, so I'm going to come down to negative 3. My slope is still positive 2, so up 2, right 1. And so now I have the line for this function. And so now we're looking to see what happened. And so one of the things that we can notice, both from the graphs and the algebra, is that slopes are the same. And so you know that means the lines are parallel. And so, again, remember that the two lines next to each other like that is the symbol for parallel. So slopes are the same, means lines are parallel. However, the y-intercept is different. So that means I moved the graph up or down because the y-intercept has changed. And so as I look from black to red, I moved down 3 units. So we can say this was a translation down 3 units. And so we can see that in the algebra. I have y equals 2x, and then I have y equals 2x minus 3. So it went down 3 units. So let's flip the page. And so we're going to look at a vertical translation just algebraically instead of via the graph. And so we are starting with the graph of y equals 3x, and we want to figure out what it would be if it's translated up 2 units. And so just like our other one, when we translated it down, we subtracted something from the end. We're going to do the same thing here. Y equals 3x, and it said up 2 units, so instead of subtracting, I'm going to add 2. And so my parent function was 3x, and I'm translating that up 2 units so I can add 2 to my output. All right. You saw a little bit with quadratic functions when we were doing piecewise things. And again, like I mentioned before, that's going to be the core of what we're doing in Algebra 2. So we're going to keep adding those in slowly as we go. And so we're going to look at another one here. How are the functions y equals x squared and y equals the quantity x minus 2 all squared related? How are their graphs related? And so if we use a table of inputs for x squared, I have x and y. If I put in 0, 0 squared is 0. If I put in -1, -1 squared is +1. If I put in -2, -2 quantity squared is 4. If I go up to 1, 1 squared is 1. +2 squared is +4. So I can graph x squared. 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. And so I'm going to sketch this parabola. And hopefully your graphs are prettier than mine. So now we're going to look at x minus 2 quantity squared. And so this time I'm going to start with 0 again. And 0 minus 2 is -2. And so -2 squared is 4. 1 minus 2 is -1. -1 squared is 1. If I put in 2, that gives me 0 inside. 2 minus 2 is 0. I square that. I get 0. If I put in 3, 3 minus 2 is 1. 1 squared is 1. If I put in 4, 4 minus 2 is 2. 2 squared is 4. And so I can graph this one. 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. And so this one looks very similar. In fact, it has the exact same shape. We just need to recognize what has happened to it. And so if we look at our graph, this one has shifted right. And so this point here at the bottom of the parabola, we call that the vertex. And so this is a horizontal shift of vertex 2 units to the right. And so you can kind of see how that happened. We shifted everything 2 units to the right, and if the vertex moves, the rest of the parabola moves with it. All right, and so one of the things you're going to notice is when we're changing something inside of parentheses in a function with x, that's typically a horizontal shift left or right. And the general form for that is x minus h, which you saw on the first page. And so if I have a minus here, that means I'm shifting right. If I have a plus there, I'm actually going to shift left. And so the next one says, write the equation for a parabola that has a horizontal translation 5 units left. And so we know that parabolas have something squared, typically x squared. But just like we had to do something to x inside the parentheses to shift right, Left is also a horizontal shift, so we need to do the same thing. Since we're going left, I'm going to add 5 units. And so this is going to feel backwards, but when I'm moving left and right and I'm adding or subtracting inside parentheses, it's going to feel like opposite. X minus 2 means right, X plus 5 means left. So let's look at another one. All right, we're going to talk about reflections now. A reflection flips the graph of a function across a line, such as the x-axis or y-axis, for any function f of x. So we first want to look at what a reflection across, and that should really say a reflection across the y-axis, reflection across the x-axis. And so when we're going across the y-axis, that's like we're changing the input value or the x value. So if I'm going to reflect this across the x-axis, the point negative 5, 1, that means I take the opposite of the input, but the output stays the same, 5, 1. So that will make this one 3, 4, this one 2, 2, and this one 0, 3. And so I'm going to graph these points, 0, 3, 2, 2, 3, 4, and 5, 1. And so as we draw this, we can see how it was reflected across the y-axis. And I'm going to do the other one in the other color again. So when we reflect across the x-axis, that's when we're changing the output or the y value. So our input value stays the same. Negative 5 will give us negative 1. Negative 3 will give us negative 4. Negative 2 will give us negative 2. And 0 will give us negative 3. So negative 5, negative 1. 0, negative 3 was in there. We have negative 2, negative 2. And we have negative 3, negative 4. And so if I graph this set of points, notice how this has been reflected across the x-axis from our original in the printed ink. So let's flip the page again. And we've got a little ways to go yet. Excuse me. So if g of x is the reflection of f of x in the y-axis, what is the equation? And so when we're reflecting, and again, this should be across. I don't really like the nomenclature in. So if we're reflecting across the y-axis, again, that's when our input is changing, but our output stays the same. So we're going to flip the x. So in other words, we're going to treat this like 2 times the opposite of x minus 1. And so 2 times negative x is negative 2x, and then we have minus 1. And so our equation will be y equals negative 2x minus 1. And so likewise, if I'm going to reflect across, that should be across there as well, across the x-axis, now we're changing the outputs. And so we're taking the opposite of everything. So we're going to take the opposite of 2x minus 1. And so we distribute the negative sign, negative 2x plus 1. And so y equals negative 2x plus 1 will be the function for the reflection across the x-axis. So let's slide down to the next example, example number 7. Here, the table below represents our original function, f of x. We don't really know what it is. And we want to find the corresponding values of g of x, which equals 2 times f of x. And so here's where this might be a little confusing. But so this expression, 2 times f of x, means I'm going to take my original output values, f of x, and multiply them by 2. So negative 2 is my original output value for f of x here. So if I multiply that by 2, I get negative 4. If I multiply 1 by 2, I get 2, and so on. So we multiply every single one of those outputs by 2. And this also tells me that g of x is the same thing, hence the equals sign, as 2 times f of x. So g of x is going to be the same as 2 times f of x. And so this is really designed, the table, to help you see how we're going. We're taking 2 times our original output, and then we're saying our new function g equals whatever 2 times our original function is. So if I graph my new g of x, I have -3 as my input, -4 as my output. So -3, -4. If I have -1 as my input, I have 2 as my output. When I have 1, I have 2 as my output. When I have 2, I have -6, 2, 3, 4, 5, and that one's actually going to be way down here. It's off our graph. And when I have 3, I'm going to have 0. And so our new function looks like I took and stretched the original one out. Example 8 is similar, except it's a compression because our value out front is a fraction. So again, we're going to do it the same way. We're going to say h of x equals half of f. And so we're first going to figure out half of f. And so -2 times 1/2 is -1. 2 times 1/2 is 1. 0 times 1/2 is 0. 4 times 1/2 is 2. And 2 times 1/2 is 1. And since h of x equals 1/2 f of x, we can just copy those values into our next column. So as we go to graph this, again, input value is -3, output value is -1. So -3, -1. -2, +1, -1, 0, 1, 2, and 4, 1. And so, unlike the other one where we stretched it, this time we kind of squished it. And that's where we get the name compression from. So let's flip our page one more time. And so here we have another example. The graph of g of x is the graph of f of x equals x stretched vertically by a factor of 3 and then translated down 2 units. What is the function rule for g of x? And so we know our original function is x. And so when we stretch, that's our a value. And so if you remember back to the front of the page, we had this general thing that looked like this. A times f of x minus h plus k. And so a is our stretch. And so it says we're stretching vertically by a factor of 3. So our a value is going to become 3. Now, we're going to be looking for a shift right or left if we're going to put x in parentheses. And so we look through, and we're not talking about a translation left or right. We're talking about translation down. So we don't need to change the x. So right now we've got 3x. And since we're translating down 2 units, we're going to subtract 2. And so our function rule for g of x is g of x equals 3x minus 2. Example 10. What transformations change the graph of f of x equals x squared to the graph g of x equals x plus 4 quantity squared minus 3? And so typically we start on the inside with the x. And so as I'm looking, I have x, but then here I have x plus 4. And so I know I'm translating left or right. And so again, remember, this is the one that's going to be kind of backwards. And so I see plus 4, so that means I'm going left 4 units. And so that's what's happening first. And then the next thing I'm going to look for is, are we stretching or compressing? But there's no coefficient out in front of this. So I don't have any stretch or compression. And so then I'm going to look at the end, and I have minus 3. So that means I'm translating down 3 units. If you wanted to, you could also graph this to help you figure it out. I'm just going to graph our final answer so you can see what this would look like. So we're translating left 4 and down 3. So my vertex is going to be at -4, -3. And so here is what my parabola would look like. And so that's continuing up over there, but it's off the graph. All right, so here are some basic rules, and this is going to be kind of where you turn when you get kind of stuck. And so if I have a function and I'm adding something to the end, this is a shift up C units, whatever that value of C was. And this would be a shift down C units. Horizontal shifts, again, are inside the parentheses, not after them. So this would be right C units. And then this one would be left C units. A reflection across the y-axis is going to have the input change. So this is across y-axis. And then if I'm changing the output, that's when I'm going across the x-axis. And so these are going to be your general rules of thumb. So if you can remember these 6 things, they're going to be really helpful along the way. All right, and so non-rigid transformations are ones that distort the shape of the graph. So the few we just looked at here are what we call rigid transformations. The size and shape doesn't change. So that's like just moving or reflecting. However, when we stretch or compress, we're distorting the graph. And so if C is bigger than 1 and I'm multiplying my function by C, this is going to be a vertical stretch by C. And then if C is between 0 and 1, that's going to be a vertical shrink by C. And so horizontal movement is going to feel backwards again, just like when we were adding inside the parentheses, we were moving left, and when you're subtracting, we're moving right. This is going to seem backwards. When C is bigger than 1, that's actually a horizontal shrink by C. And when C is between 0 and 1, this is actually a horizontal stretch by C. All right, so that's kind of the end of our notes. And so not a lot of practicing here from those. The next worksheet is going to be your practice for this section. Please keep referring to your notes to help figure this out. Feel free to work with a classmate and ask questions while you're here. Feel free to work with it. So let's look at some practice. We're going to take one function and give it some practice. So let's say our function is f of x equals x cubed. Let's call that our parent function. And then we're going to see what we can do to that. So x cubed, if I build a table of values, we have -2, -1, 0, 1, 2. So x cubed is going to look like this.
Oh my God, we love you above all things with our whole heart and soul because you're all good and worthy of all our love. We love our neighbors as ourselves with the love of you. Forgive all who offended us and yes,
and so -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. And so our cubic graph looks a little bit like this. If I add something in the middle, I'm shifting it horizontally. And so this -1 means I'm going right 1 unit. So my graph is going to have the same shape, but it's been shifted. And so if I also add something to the outside, I'm also shifting it there. So now I'm not only going right 1, I'm going up 2. And so right 1, up 2 puts my vertex there. And so my next one is going to look something like this. And lastly, I'm going to compress it so I can get more of this on the page. And so we'll take 1/2. And so I've moved the vertex, and then I'm compressing it by 1/2. So it will look something like this. So there is just kind of a summary of how any graph can move. So flip the page over one more time. And so you've got your functions of families homework. And so you're going to work through all 8 on that page and all 8 on the next page. You can feel free to work with a classmate and make sure to ask